Hello, my name is Sofia Alonso,
And I'm Meaghan Desilets.
and this is our instructional video project for BMED 2210, and we will be talking about ideal gases. The first thing that we're going to be talking about is what is an ideal gas. So there are two assumptions to define an ideal gas. The first one is that the intermolecular interactions between the molecules are negligible. This means that all the collisions are elastic and that the molecules aren't reacting with each other. The second assumption that we must make is that the volume of the individual molecules is negligible. So this means that they aren't occupying any space. Of course, we know that in a real gas, these assumptions don't hold to be true, since the gases do occupy some space, so their volume is not zero, and they do interact with each other to some extent. However, these simplifying assumptions allow us to approximately predict the behavior of real gases and to complete calculations using the ideal gas law, which we have stated here. So the ideal gas law is PV equals nRT, where P is absolute pressure, V is volume, N is the number of moles, R is the ideal gas constant, and T is the temperature. And using this equation, we're able to describe certain relationships between these properties.
Okay, so there are some conditions where you can use the ideal gas law and some where it's not really an appropriate assumption. So sort of like the ideal conditions for a gas are defined as standard temperature and pressure, which is when temperature is 0 degrees Celsius or 273 Kelvin and pressure is 1 atmosphere. Even when these conditions vary slightly from standard temperature and pressure, it's still okay to use the ideal gas law, but they have to vary in specific ways. So for temperature, it can be higher than standard temperature, that's fine. But if it gets too much lower and it starts nearing the condensation point of the gas, then the molecules are getting closer together due to the condensation beginning to happen, and they're interacting with each other more and more, and so the forces between them are no longer negligible. It's okay if pressure deviates down from standard pressure, but if it deviates too far upward, then a similar situation occurs where the molecules are getting too close together due to this increased pressure, and their interactions are also no longer negligible. Okay, now we'll look at a couple of problems where we look at the ideal gas law and how it can or cannot be used.
So first we're going to talk about a problem where the ideal gas law is an appropriate assumption. So this problem analyzes the breathing of a person at sea level. So you have a stream of air being inspired, you have a stream of air being expired, and you have a stream of gases being transported from the bloodstream to the lungs. You also know the volumetric flow rate of the inspired rate and the molar composition of the inspired stream and the expired stream. In addition, you also know the two temperatures of the inspired and the expired stream, and you can also assume that the pressure is equal to 1 atm since this person is at sea level. So what you're trying to find right now is the mass composition of the stream of air being transported, of the stream of gases being transported from the bloodstream to the lungs. So in this problem, PV equals nRT is an appropriate assumption. So you would be able to use this to find the number of moles in the inspired air, in the inspired stream, since you know the pressure, you know the volume, and you know the temperature. So you'd be able to find the number of moles. And the reason that this is an appropriate assumption is because the temperatures are both near the temperature of STP, and also they are so far away from the condensation point of these compounds that it is an appropriate assumption to assume that the ideal gas law can be used.
All right, now we'll look at a problem where the ideal gas law can't be used. So we're looking at a process of converting natural gas into a liquid for better transportation. So we're given the temperatures of the streams. This is stream 1, this is 2, and this is 3. And we can assume that this temperature also applies to this stream because they're both coming out of the same cooler. So we're given let's assume that this is happening at sea level. So pressure is 1 atm or close to it. And we want to find eventually the volumetric flow rate of this stream. We'll set a basis for the first problem. So that will be equal to 500 liters a minute. And let's assume that we're given the molar fractions of, or not that compound, I'm sorry, just these ones. So using the ideal gas law, we can find the total molar flow rate of stream 1. This is because we know the pressure, we know the volume, and we know the temperature, very similar to the last problem. And also because this temperature is far from the condensation points of the gases. So once we find n, we can calculate mole balances to find the moles of all of these compounds. However, that's not what we're looking for in the end. What we want is the volumetric flow rate of this stream, but because this temperature is so low, it's very close to the condensation point of these gases, and the intermolecular interactions are no longer negligible, so we can't use this equation a second time. Were we given the van der Waals constants for these compounds, we could use this equation, which is the real gas equation, but we weren't given them in this problem, and we're not really going to get into that today, but that's what you would do if you wanted to solve it.
So that concludes our presentation on the ideal gas law. I hope this was helpful, and thank you.